Hallo miteinander! Alle Mitwirkenden in diesem Film wünschen euch einen gut gelaunten Weltkarnivorentag 2022, für den wir spannende Filmbeiträge zusammengestellt haben. Im Mittelpunkt stehen dabei die selbst für Wissenschaftler immer wieder überraschenden schnellen Klappfallen, Katapulte und Fangblasen, sowie eine elegante Methode, die im Labor Kreuzungen und Verwandtschaften beim Sonnentau sichtbar macht. Hallo, wo ist denn hier die Spülung? Wir legen gleich los mit den ausgeklügelten Fallen der laut Darwin wunderbarsten Pflanze der Welt, der Venusfliegenfalle. Diesen Film erstellten Irmgard und ich zusammen mit unserem langjährigen amerikanischen Freund, dem Veteran der Dionea-Forschung, Emeritusprofessor Stephen Williams. Wir alle kennen aus dem Fernsehen oder auf YouTube Filme, in denen Fliegen von Nektar angelockt an süßen, dicken Tropfen in der Falle naschen, bis diese zuklappt. Alle von uns kennen das. Aber es gibt begründete Zweifel daran, dass dieses Szenario auch den Abläufen in der Natur entspricht. Ups, jetzt aber raus hier. Zwar zeigen Beutezählungen in Wohnungen, Gewächshäusern oder in der Nähe von Landwirtschaft bis zu 90% Fliegen. Ganz einfach, weil sie dort hauptsächlich vorkommen. In der freien Natur sieht das jedoch ganz anders aus. Untersuchungen von Stephen Williams und anderen in den Carolinas und in Florida zeigen eindeutig 70% Beute aus Spinnen, Ameisen und Käfern. Das bedeutet, Dionea ist ein Generalist, der nur selten Fliegen fängt. Auch die Darstellung, dass diese aus der Ferne durch süße Nektartropfen angelockt würden, trifft nicht zu, denn die Fallen der untersuchten Wildarten waren trocken, was zahlreiche Fotos bestätigen. Es kommt noch besser. Weder Nektar noch UV-Reflexion oder die oft zitierte Fleischfarbe der Falle scheinen eine Rolle zu spielen. Die Venusfliegenfalle lockt offensichtlich keine Beute aus der Distanz an. Steves und Bill Scholz' jüngste Forschungen ergaben eine überraschend niedrige Fangquote. An durchschnittlichen Tagen fingen nur 1,5% der Fallen des Standorts Beute. Das widerspricht sehr deutlich einer effektiven Anlockung, wie wir sie etwa von Drosophilum kennen. Stark nässende Fallen gibt es tatsächlich, was mich vor einigen Jahren sehr überraschte, denn die Dionea in unserem Garten sehen aus wie der Wildtyp mit trockenen Fallen. Ich suchte daher nässende Fallen und fand auf Größe gezüchtete sogenannte B-52s sowie wegen ihrer mutierten Sperrborsten beliebte Shark Teeth. Beide wurden recht schnell von zuckerliebenden Rußpilzen befallen, die in den Fallen schwarze Beläge bilden. An Naturstandorten ist so ein augenfälliger Pilzbefall höchstens eine Ausnahme. Möglicherweise wurde durch Züchtungen ein empfindlicher Mechanismus gestört, wodurch die Drüsen am oberen Fallenrand zu saften beginnen. Beim Wildtyp findet man das nicht, wie Steves Feldversuche zeigten. In trockenen Fallen fanden Wissenschaftler Spuren von Fruchtaromen. Offensichtlich bilden die Drüsen am oberen Blattrand eine Art Geruchsspur, die für Fliegen und Ameisen so interessant ist, dass sie dem Pfad entlang der Drüsen bei ständigem Kontakt mit den Mundwerkzeugen folgen. Dieser Pfad entfaltet seine Wirkung erst aus der Nähe, wenn potenzielle Beute die Falle betritt. Folgen kleine Tiere dem Pfad, werden sie oberhalb der Triggerhaare in der Blattmitte geführt, ohne diese auszulösen. Sind sie aber groß genug, schnappt die Falle zu. Dieses Verhalten lässt sich oft beobachten. Besonders die kleinen, in ihrem Lebensraum häufigen Ameisen sind für die Venusfliegenfalle ein ernstes Problem. Das Schließen und Öffnen der großen Fallen kostet viel Energie. die zu kleine Ameisen schlicht nicht liefern. Um diese Energieverschwendung zu verringern, entwickelte die Pflanze einen ausgeklügelten Mechanismus, den wir zufällig dokumentieren konnten. Direkt neben den Dionäer in unserem Garten bauten kleine Ameisen der Art Lasius neglectus ihr Nest und liefen permanent durch die adulten Fallen. Wir rechneten damit, dass in kurzer Zeit alle Fallen geschlossen wären, aber genau das geschah nicht. Ein Grund, mit unserer Kamera genauer hinzuschauen. Wie von Frank Jones schon vor rund 100 Jahren beschrieben, folgten die Ameisen fast immer dem Pfad entlang des Fallenrands mit den bei unseren Pflanzen trockenen Drüsen. Mit höchstens 3,5 mm Länge hält sie das sehr effektiv von den Triggerhaaren fern. Selbst wenn sie den Pfad nach unten verließen und versehentlich ein Triggerhaar berührten, löste das die Fallen nicht aus. Offensichtlich sind Ameisen clever genug, nach der ersten Kollision zumindest nicht innerhalb der nächsten 20 Sekunden ein zweites Mal gegen das Hindernis zu laufen. Daher werden sie nur sehr selten gefangen. Das wirft ein neues Licht auf die Tatsache, dass die Venusfliegenfalle sich erst nach 2 Berührungen der Sensorhaare schließt. Wir zählten rund einen Monat lang mehrmals täglich, jeweils 10 Minuten lang, wie viele Ameisen die Fallen unbehelligt passieren. Die Datenmenge reichte aus, um recht zuverlässig berechnen zu können, welches Risiko eine kleine Ameise wie Lasius neglectus hat, in einer ausgewachsenen Falle gefangen zu werden. Erstaunlich niedrige 0,04%. Damit ist das Risiko einer kleinen Ameise in einer Dionäerfalle umzukommen rund 2,5 Mal niedriger als das eines Patienten in einem deutschen Krankenhaus an einem Behandlungsfehler zu sterben. 0,1%. Dieser ausgeklügelte Mechanismus zeigt einmal mehr, dass Dionäer von Charles Darwin völlig zu Recht als wunderbarste Pflanze der Welt bezeichnet wurde.
Whether hot chilies or sweet sugar cane, it is the ingredients of the plants that determine their biological activity by means of a certain chemical structure. This also applies to the sundew, which protects itself against herbivores with poisonous corrosive substances called naphthoquinones. A special feature here, however, is that a common precursor substance with similar but distinguishable molecule halves can react to form 2 so-called isomers. The chemist calls these 2 isomers plumbagine and ramentasseone. But in order to be understandable for the non-chemists as well, let's think of these 2 isomers as mopeds with a saddle on either the rear or the front wheel. The isomers can be easily separated and distinguished by chemical analysis. A special significance for the chemical differentiation of sundew species arises from the fact that almost all so far determined species only form one of the isomers. In order to stick with our picture, that means either front or rear seaters. Crosses of species with different isomers, on the other hand, produce both front and rear seaters. In the chemistry of natural products, this is a rare exception that allows simple hybrids to be identified directly by means of chemical analysis. Usually, closely related species produce the same ingredients. It becomes interesting, however, when both isomers occur within a species group. The longest known example of this kind is the pair of roundleaf sundew, Drosera rotundifolia, and spoonleaf sundew, Drosera intermedia, in which the first species contains ramentasseone and the second contains plumbagine. The very rare natural hybrid Drosera hybrida eloisiana actually contains both quinones. So to stick with our comparison, front and rear seaters at the same time in approximately the same quantities, which was discovered in 2016. Further examples of different isomers in a species group were found a short time afterwards in the kinship of the Indian sundew, Drosera section arachnopus, which has its greatest diversity in Australia, although this has only been recognized since 2001. Here most species form plumbagene, some form ramentation, and only a few form both isomers. The true Indian sundew, Drosera indica, belongs to the latter, and it is, as far as is known, the only species of the group that reaches as far as Africa but does not occur in Australia. The systematic investigations of different sundew sections for their naphthoquinones that have been carried out since 2016 have also led to new findings in the pygmy sundews from southwest Australia and their larger relatives, the Drosera petularis group from northern Australia. According to earlier investigations, these were considered devoid of quinones, which has since been refuted several times by new evidence. Therefore, today there is no longer any larger group of species that is characterized by a complete lack of naphthoquinones.
Der mehrere Kilometer lange Pfad zum Standort wird selten genutzt und ist vielfach von Vegetation überwuchert, durch Erosion abgerutscht oder besteht aus knöcheltiefem, glitschigem Lateritschlamm. Nur an wenigen Stellen dringt Sonnenlicht durch das Blätterdach bis an den Boden. Die lichtempfindliche Digitalkamera lässt das herrschende Dämmerlicht viel heller erscheinen. Fotografieren ist nur mit Blitzlicht möglich. Drosera schizandra ist so sehr an die hier herrschenden Lichtverhältnisse angepasst, dass er im Gegensatz zu den meisten anderen Sonnentau direktes Sonnenlicht nur schlecht verträgt. Die bis zu 20 cm großen Pflanzen wachsen auf der den Regenwaldboden bedeckenden Schicht vermodernder Blätter, kaum jedoch auf freiem Lateritgrund.
In the rainforest-dwelling sundew species from Queensland in northeast Australia, Drosera section prolifera, 3 of 4 known species have so far been examined for naphthoquinones. Ramentation was detected in 2 species, plumbagene in 1, Drosera prolifera. As expected, both quinones were found in the artificial hybrid between Drosera prolifera and Drosera schizandra, which also confirmed the reliability of the analytical method. Since the 4th species, Drosera bubugujin, which was not described until 2020 and has not yet been investigated chemically, shows some characteristics of this hybrid, knowing its quinones would be highly informative for clarifying its relationships. Is it really a species of its own, or is it a hybrid?
Happy World Carnivorous Plant Day. My name is Simon Poppinga. I work at the Botanical Garden of the Technical University of Darmstadt in Germany, and I'm doing research on carnivorous plants and plant movements in general and how these systems can inspire future technologies. And this is also the topic of my little talk for today. When we talk about movement, for example, in technical systems, think of a car door or your foldable laptop, and also in most animals, you will find rigid body mechanisms like this. This is a hinge system which is composed of two stiff elements which are connected and which can move against each other, but which do not deform by themselves. This is a so-called rigid body mechanism which you can find in most technical applications, but also, for example, in my arm. It's also a rigid body mechanism. These systems are, from a technical viewpoint, not really good because they tend to break due to wear. Repetitive loading cycles, movement on, and suddenly it breaks. And we know this also from our hinges in the knees or in the elbow. From time to time, it doesn't really work any longer and you have to go to the doctor. So, is there another solution for technical applications to help them overcome this structural problem of hinges? Indeed. We find it in nature, in plants. When you look at a plant, this is an early flower here in spring in Darmstadt, these are completely motile systems. They can follow the sun with their leaves and the flowers, they can bend their leaves, but you won't find any of these rigid body mechanisms in such a plant. So how does it move? It's a very different system, and it's termed a compliance system, because structures in plants that move deform in their entirety, or at least at certain areas of their motile structures. What does it mean? Let's take, for example, a pine cone. This is a sugar pine from the United States, a very large pine cone. And maybe you have already witnessed that a pine cone is open in the dry state and closed in the wet state. I've prepared a closed pine cone here. The water drops, you can see it's completely wet and it is closed. This is a purely hygroscopic effect which dictates that the seed is not released when it's unfavorable, it is wet, but only released when it is dry and the wind can take the seed away. And each of these little scales here deforms, it bends in its entirety, and it does not show any of these rigid body mechanisms. And the interesting thing is, this is a very, very repetitive and very, very resilient movement. Even pine cones from the Middle Miocene, about 16 million years of age, can still move. There's a study out there which shows this. And this hygroscopic movement you can find in many, many other plant structures. For example, in seed capsules. You might be aware of what this is. Ibicella or Proboscidea have these capsules which split open hygroscopically. Or you can find it in the false rose of Jericho, which also opens and closes due to hygroscopic effects, just by bending and not by incorporating rigid body mechanisms. Another example is the weather thistle. Another mode of actuation, this is how we term this effect which drives the motion, are active turgor changes, which means that in some occasions the plant is capable of dictating cellular pressure by varying the water content in special motor cells. This is, for example, what the sensitive mimosa does. When you touch it, it will fold its leaves because the turgor states in specialized cells will change. The speed of hydraulic motion is size dependent, which means the larger the structure is, which is actuated hydraulically, the slower it moves, and the smaller it is, the faster it becomes. This is easily understandable because, for example, if you consider my arm as an hydraulic structure, You can easily imagine that water needs much more time to travel or to diffuse through my arm than it does in my finger. Yeah? So this is the size dependency of such hydraulics, yeah? Which means that we find large structures like a pine cone which move in the hours regime, and we find small structures which are based on turgor changes, yeah? Which can move in the millisecond regime. And now it's getting interesting because we have a very particular carnivorous plant which does exactly this. And this is the pimpernel sundew, Drosera glanduligera. You might know it, it's from Australia. Yeah? It's a very, very unique and specific prey capture mechanism. Additionally to the otherwise typical glue tentacles, which bend hydraulically rather slowly when touched, we find additionally marginal snap tentacles, which are glue-free and which, when a prey touches these tentacles, which rapidly bend inwards and catapults the prey onto the trap leaf center. This is a very, very nice and spectacular capture mechanism. Yeah? And as far as we know, these movements of these small tentacles are purely hydraulically and are in the millisecond regime. 75 milliseconds. This is even faster than the Venus flytrap, but the Venus flytrap is larger, of course, and has some other tricks which I will introduce you in the following. Another means of actuation, and now it's getting fast, is the release of previously stored elastic energy, elastic relaxation. This is similar to a mouse trap, so to say. Yeah? This is a nice example of how pre-stress can be used to generate very, very fast movement. And this is what plants also do. By growth processes or other means, pre-stress is generated, like I'm doing this here in this mouse trap. Yeah? I'm putting this down and I store pre-stress. And by a certain trigger, this pre-stress is released and a very fast motion response leads, for example, to the trapping of a mouse, or in the case of the Venus flytrap, to the capture of a prey animal. Yeah? These elastic relaxations are very, very interesting. Yeah? You can see, for example, here a special case which is termed snap buckling, a snap-through process where the curvature, the three-dimensional curvature or the double curvature of a structure suddenly changes. And this can also be applied to generate fast movement. You will see a very swift jump response of this structure. Woo! Yeah, you can see these reactions with elastic instabilities can be really, really swift and fast and also forceful. Some plants disperse their seeds by such means. Think of the exploding fruits of the touch-me-not. Yeah? Some plants make use of such elastic instabilities to capture their prey, the Venus flytrap, for example. Or think of the bladderwort, Utricularia, which applies a similar deformation and relaxation behavior. And these are all systems which are termed compliant mechanisms because they don't have rigid body mechanisms in their structures. And these systems are, of course, on the first hand, of a reduced mechanical complexity in terms of the structural components which you need to build them. You don't need fasteners or springs or whatever. You can make it out of one structure. It's one structure which is capable of such a fantastic movement. Yeah? And it is very likely that these mechanisms are very durable and functionally resilient, yeah? Because they can move over certain cycles without any fatigue or wear. And the thing is, we make use of these principles to find solutions in technical problems or in technical applications. For example, one question we followed was, how can we design a biomimetic flapping mechanism which could, for example, act as a gripper in soft robotics or, for example, as a facade shading element. Yeah? And we came to the solution with such a deformation principle. You can see this is just a sheet of paper. It's a postcard from our botanical garden. Yeah? When you apply a certain origami folding curvature here and you apply pressure, it will snap. And probably this movement reminds you of something. This already looks like a snap trap, but it's not that of a Venus flytrap, because a Venus flytrap has this very, very swift and forceful snap buckling instability. This is the deformation principle which we find in the water wheel plant, Aldrovanda vesiculosa. It's a very continuous and very, very smooth movement, yeah? Whereas the Venus flytrap just knows open and closed and no intermediate state. Here we can design a flapper which can move and stop in any transitional phase. Yeah? This is quite nice. And these are systems, yeah, which are extremely promising for technical applications. And we are designing these together with architects, construction engineers, material scientists, and so on and so forth. To sum up, plants are really the masters of motion. They don't make use of rigid body mechanisms which tend to fail over time. And carnivorous plants in particular are very, very spectacular because they show all types of actuation principles and motion responses also in terms of velocity, which makes them a very, very promising and very nice topic to study from a biomechanical and functional morphological viewpoint. Thank you very much.
Wo ist denn hier die Spülung?
Du stehst los.
Ups, jetzt aber raus hier.
The International Carnivorous Plant Society wants you to be successful with your plants. We welcome growers just getting started all the way through professional scientists. We started an annual World Carnivorous Plant Day to celebrate these spectacular plants. Take a look around our website and you'll find historic documents about carnivorous plants, growing guides, free educational resources, and more. Have questions? Ask. We don't bite, but our plants do.